speaker. We'll discuss the think points of random walks and the GFF.
Okay, thank you very much. Thank you, the organizers, for this nice conference. And yes, so today we'll talk about thick points of random walk and the Gaussian free field. So I have done this work under the supervision of Nathaniel Beresky, and I would like to thank him for the time he dedicated to me. So I'll start with some notations. YT here will be a random walk on ZD, starting at the origin, and D will be a dimension greater or equal to 2, and I will consider a big box, like a big box Vn of side length 2n plus 1 certain at the origin, and tau n will denote the first exit time of Vn of this big box. And so I will look at the local times, Lxt, which is just the total amount of time the walk has spent at the vertex x before the time t. And here's a picture. Hopefully we can see something. So when it is basically white or really pale, it means that the walk didn't go there. And if we can see something, it means that the walk has accumulated some local time in the point, and basically I will be interested by the points there, and I want to know how many points are there, for instance. So here it was in dimension 2. In dimension 3, the pictures are even worse. Okay, so my talk will be divided in 3 small parts. First, I'll talk about the dimension 2, then I'll talk about higher dimensions, and finally I will come back to the dimension 2 and I will try to give the main ideas of the proof. Okay, so let's get started with the dimension 2. Okay, so here YT will be a continuous time random walk on the square lattice, rate 1, so it means that the walk waits an exponential amount of time in each vertex and then jumps. And the jump process is encoded by the random variable xi, which are just IID centered with finite variance. And we denote sigma, the covariance matrix of the jumps. And there is a result by Dembo, Perez, Rosen, and Zaintuni in 2001, who showed that if we assume that x has all the moments finite, then we know the behavior of the maximum of the local times. Okay, so Lx tau n is the local times, and we kill our walk after it exits for the first time the big square. And so here we have constant times log n square. Okay. So this is unusually big because typically the local times will be more like log n. And also we can now consider the set of A thick points. So if A equal 1, so A equal 1 corresponds to the maximum of the local times. And here we look at the points x, where the local times is really big, so bigger than a fraction of the maximum. And the result is the following. So they showed the same thing. If we assume that all the moments are finite, then the behavior of the number of thick points is the following. So roughly speaking, it is n to the power 2 times 1 minus a plus little o of 1. So for instance, this result doesn't tell us anything about logarithmic corrections or something like that. In the continuous world, this result would be to say the Hausdorff dimension of the thick points. So just a comment, what they did is that they first derived this result for the thick points of occupation measure of the Brownian motion. And then the discrete case is deduced by strong coupling arguments. And these arguments require all the moments to be finite. This is why we assume this. And they ask a question, is this result still true if we assume only the second moment to be finite? And as I tried to explain a little bit, their approach can't really give the result, and we need a different approach to solve this problem. And this is what I did. So now we are exactly under the same setting, but we assume only the symmetry and okay. So we only assume the jumps to have finite variance. Moreover, we assume the jumps to be symmetric, and then the two previous results still hold. So the two previous, just the result on the number of thick points and the result on the leading order of the supremum. Okay, so in my title I had the word Gaussian free field, and actually my proof relies on the connections to the Gaussian free field. And this is why we have to assume X to be symmetric, otherwise we cannot define an associated Gaussian free field. So I will talk a little bit more about the proof in the last part. And also I want to mention the fact that actually this result also holds in a really general or fairly general setting, including, for instance, isoradial graphs. Now we'll talk a little bit more about higher dimensions. Okay, so here the dimension D is greater or equal to 3. YT is a continuous time simple random walk with weight 1 on ZD. So here we are in a less general case. We just consider simple random walks. And then I define G to be the green function, the value of the green function on the diagonal. So this quantity here is finite because we're in dimension greater or equal to 3. And the result is the following. So I computed the leading order of the local times. So computing this is not new, but we can actually say something more precise than in dimension 2. And if we recenter the supremum of the local times, then the quantity will converge to a non-degenerate random variable L. And actually L is a randomly shifted Gumbel variable. So randomly shifted just means that the location of the peak is itself random, the location of the peak of the Gumbel variable. And again, we can consider the set of A thick points. So the points which are where the local times are larger than a fraction of the maximum. So A equal 1 again corresponds to the maximum. And we have the following result, so which computes again the number of thick points. And again, so we have the Hausdorff dimension, which is 2 times 1 minus A, but we have something even more precise, because actually this converges to a non-degenerate random variable MA. So just a small comment, actually MA, the distribution of MA does not depend on A if A is strictly less than 1, is positive and finite homothetically. And for A equal 1, M1 is just finite homothetically. We cannot expect M1 to be strictly positive, almost surely, because in my previous slides, L here can take arbitrary negative values. So it means that Mn1 here can be empty. Okay, so just one comment on that. If we start from the vertex x, the local times Lx tau n is just an exponential variable with mean which is almost equal to g. So this is actually really accurate if x is in the bulk of our big box Vn. And the two previous results actually say that the field composed by the local times behaves like the field composed of IID exponential variables located at each visit vertex by the walk. And now I'll try to be a little bit more precise about this argument, and I will talk about point measure. So the idea is to encode the A-thick points in the following point measure. So this idea is not new, and for instance we can this has already am I supposed to do something? Okay, perfect. So this idea is not new, and we can, for instance, see this result for the discrete Gaussian free field in dimension 2. This has been done by Biskup and Wheeler. So here, the point measure nu and a. So we have first here a renormalization factor, and then for each point in my box, I just scale it so that the box now lives in the small box of side length 2, and the local times is also shifted by minus 2ga log n. So nu and a has to be viewed as a random measure on minus 1, 1 to the d times r. And I want to compare this measure with the field. So Ex will be just IID exponential variable, which are independent of our random walk y. And now I define mu and a to be another measure, and it is exactly the same thing as before, but now the local times is replaced by the exponential Ex, and we put a point only where the walk has been. So x visited is x visited by our walk y. And the result is the following. Actually, for all a between 0 and 1, so included 1, the two measures converge in distribution, and actually the two limiting limits are the same. Do you have any question about that? Okay. So now I will come back to the two-dimensional case, and I will try to give you the main ideas of the proof. So just to recall you the settings the following: we have a continuous time random walk on Z2, rate 1. The jumps are xi, iid, finite variance, sigma is the covariance, and m and a is the set of a thick points. So just the local times are larger than a constant time log n square. And we want to show the following result, so we just assume the symmetry and again finite variance. So first of all, the upper bound is actually easy. So the upper bound is just to say that we don't have too much thick points with high probability, and this is really the easy part, and you just need to compute the first moment. So we'll just talk about the lower bound, and the lower bound we want to say that we have a lot of thick points with high probability. So as usual, this relies on the second moment method. So just to recall you, if z is a non-negative random variable, and if we want to show that z is greater or equal to half, say, than the expectation of z, then we just need to show that the expectation of z square is not too big, and the expectation of z is big, so that our variable is fairly concentrated. Okay, so if a is in between 0 and 1/2, actually you can apply directly this inequality to z equal just the number of thick points, and this will work. So the first moment, as I said before, is easy to compute, and if we want to compute the second moment, in particular, we need to control this. So just the probability that the local times in two different points are big. So my point here is to say that this can be done, it's not so hard, but it's not in one line. And if we had the Gaussian free field here rather than the local times, actually this is just really straightforward because it's part of the definition of the Gaussian free field, because it is a Gaussian vector. And all the idea of my proof is to actually exploit these kind of things, and to say that if we had 1/2 of the Gaussian free field square rather than the local times, everything would be simpler. And of course, if a is larger than 1/2, actually the second moment explodes, and as usual, we have to do some truncations. And actually, it is here that the problems start. Okay, so I told you that I want to exploit the links between the local times and the Gaussian free field. So for that, there are a lot of different isomorphisms, and actually the most convenient for me will be the Eisenbaum's isomorphism. And this is what I'm going to explain to you. So here phi n will denote the Gaussian free field, on the big square Vn associated to the walk yt. So again, we have assumed that the increments are symmetric, so we can define this Gaussian free field. And the boundary conditions will be just Dirichlet boundary conditions. And here, E will denote the associated expectation. So the result is the following. So like that, it doesn't look really nice. So I don't want to put this without writing this. So this doesn't mean anything, but this is how I like to think about this isomorphism, because on the left-hand side you have the local times, and we added half of the square of the Gaussian free field, and on the right we roughly have half of the square of the Gaussian free field. So when I write this, I neglect the impact of S, and I neglect the impact of this shifting, this shift here. Do you have any question about this isomorphism?
What is the role of S here?
Because here, for instance, we can't take S equals 0, otherwise here we would have something equal. I can't divide by 0.
I know, but you said you discard this term sometimes.
Yeah, I mean, if you want, I first delete this term and then I take S equal to 0. So of course this doesn't mean anything, it's just that I want to, actually we just need to think about this isomorphism like that. For instance, this isomorphism tells me something like the local times Lx tau n are stochastically dominated by half of the square of the Gaussian free field. So of course it is not completely true, we have a shift, but actually this shift in my computations is not important. Yes?
Yeah, maybe you can say just that one way to interpret it is just via, because the square of the Gaussian free field can be interpreted as occupation time of fluxus, and when you add the other one, then corresponds to excursion from the boundary, and when you're inside, basically the two things are absolutely continuous, basically. I think something like that.
Okay.
This is what you.
Okay. And so, for instance, this isomorphism is really convenient for me because in the previous slides, I told you that I wanted, for instance, to compute this, and with the isomorphism, I can just say that this probability. So I want to show that the second moment is small, and the isomorphism tells me straight away that this probability is actually smaller than the probability that the Gaussian free field is big in two different points, and this is a one-line computation. Okay. So now I'm going to talk about the truncations I need to do. So I take S equal 1 in the previous isomorphism, and I just take phi n, an independent Gaussian free field. And of course, my good event at X will be decomposed in two good events. So I will have first a good event linked to the local times, a second, a good event linked to the Gaussian free field. And, okay, so I will try to be brief. So the first good event is just to say that we want the local times at X to be big, but we want to be never too thick, actually, around X. So this idea is similar to the idea of Nathaniel Beresticki. He did that for the continuous Gaussian free field. And then for the Gaussian free phi n, we just require it to be typical. So we don't want at all the Gaussian free field to be thick at the point X. So here I'm just more precise. I take CR square centered at X, radius R. And then for B, which is slightly larger than A, I define the good event linked to the local times to be, so here I just require my local times to be thick, and then I add this. So here I just require my local times to be neither too thick for all the scales, because here B is just slightly larger than A. And for the Gaussian free field, it is exactly the same thing, but I don't want it to be thick, so here I can put something which goes to 0. And then we are basically done, because we can apply the second moment to the truncated version of M and A, and then we just need to compute the first and the second moment. And to do that, we transfer all the technical computations from the local time to the Gaussian free field using the Eisenbaum isomorphism. And actually, it is really important because if we didn't use the isomorphism, trying to estimating this is actually not really simple because L is not Gaussian. So if we want to estimate this, we would probably do something like looking at the excursions between different circles. And if we do that, actually, we will just do the Dembo-Perez-Rosen-Eisentuny method, which is not convenient in our case. Okay, so I think I will stop now. Thank you.
Any question?
In a way, what is in the core of this isomorphism which makes a method work?
What?
What is in the isomorphism which is hidden there, which makes the method work?
Actually, I don't know so much about this isomorphism. And for instance, the only proofs I know about this is we take the moment on the left-hand side and we take the moment on the right-hand side, and then or we do the same thing with the Laplace transform, and then we actually we notice that these two quantities coincide, and I don't have a good interpretation, and I guess Wenlin has a better interpretation.
I mean, you use the Legendre type approach to these square of the Gaussian free field boundary conditions, and sort of it gives a way to explain. So you have a boundary value and you interpret it as, instead of saying you add the harmonic function, you say you add a Poisson point plus the excursions into the inside, and then okay. So there is another. So that would be my question, sort of how, because then this is other approaches somehow related to the random walks itself. So maybe there's a way to relate what you did to the other approach. Might be
interesting. I have one question. In higher dimension, you have a limiting law for the thing points.
Yes.
Do you know the limit law? You said that NA.
So here?
Yeah.
So my approach here was to, because we are in dimensions greater or equal to 3, so we can take basically all the moments. We are not like in dimension 2, where we have a L2 face and a non-L2 face. So in dimension 3, we can actually take all the moments here, and I show that all the moments converges. And MA, so I don't have MA doesn't have a simple distribution, but I know all the moments of MA. And actually, the moments are not really bad because they encode the path of the walk actually. So yeah, so MA is characterized by all its moments.
Okay, if there is no further question, we can just figure it out.